Today we have Vukash and Matthias from Aurea, and they're going to cover Dockerizing Aurea. So Vukash and Matthias, take it away.
Thank you.
Okay, thanks. Hello, everyone. So, as the presenter said, my name is Matthias and Vukash. I'm a software engineering manager, and Vukash is a chief Docker architect. We work together in Aurea software, and we run a team that is responsible for the Docker infrastructure. And today we want to share, if this works, yes, what we're doing for the past year. We've been running Docker in production for a year, and we want to share what goals we set for our team, which are the results that we got, and we are going to see some of the technical challenges that we solved in the way. So, look backward. Yeah, maybe you can help me. So, Aurea, it's a company that has a dozen of enterprise products for different domains. So we work with IT companies, pharmaceutics, marketing. We have many applications. It's a remote-first company. So actually, I just met Vukash for the first time yesterday in this DockerCon. So fun. Yeah, just use this. So we set 2 goals for our team. And one of those was to, of course, decrease computing expenses by consolidation and simplification. So I'm going to explain how we achieve that. And the secondary goal was to improve our operational team's productivity through standardization. So if you can look at this graph, in the first one, we see one application running on a single host, which has 2 CPUs and 1 GB of RAM. And in the graph, the green line is the CPU utilization, and the yellow line is the memory utilization. And as we can see that for this particular application, even though we are paying for the whole piece of the infrastructure, on average, we are utilizing just 21%. So how we could improve the utilization of what we are paying for? So we could use instead a smaller VM, but if we look at the CPU graph, we can see that this application is already picking over 50%. So we will decrease from 2 CPUs to just 1. This application might not work properly. So what we could do is just use Docker to use a more powerful VM, and use Docker to run several applications on the same host. And what happens when we do that? So if we look at the second graph, we can see that this is one host with 128 CPUs, 2 terabytes of RAM. And we can see that the average to-peak utilization is much slower than with a single app. And that's because the utilization of all the applications kind of aggregates in such a way that the peak on each single application has less impact on the whole host resources. So with this smaller average to peak utilization, we can get a higher average utilization. So this host has 74% utilization. Okay, and about our secondary goals, how does Docker help us with this? So we have, our ops team needs to deal with different products. So each product might be in different technology stacks and have their own rules of how you need to deploy them, how you need to do standard operations as a simple restart. And of course, for each of these products, we have runbooks that says, okay, for this product, you need to follow these steps or use this piece of automation. But with Docker, what we can do is abstract all this complexity using Docker files, Docker Compose files, and for the ops team, just by running with simple Docker client commands, they can do most of the work, like provisioning a new version of the app. It's just Docker Compose app, or doing Docker restart to restore service or reload some configuration. This is still not working for me. So what are the results that we have achieved in the past year? So we've done Dockerized many products, and we've been replacing more than 2,000 VMs with 1,900 containers. That allows us to decrease our infrastructure costs from 13 million to 6 million, and these are the AWS costs. And we were able to increase the utilization, the average utilization, from 5% to 72%. So far, it seems similar to some of the results that other companies are reporting. So we wanted to share some of the strategic decisions that allow us to reach this goal quite fast. And one of those is that, first of all, we've decided to focus on the basics, technology, and just go with the simple Docker engine. We tried out Swarm and ECS in the past, but we found it a little bit harder to adopt for our ops and engineers. And also, many applications had to be a little bit re-engineered to be able to run in the cloud. So with just using simple Docker, we can do like a neutral change from what we were already running on a VM to what we can run on a Docker host. And this speeds up the process. Another strategic thing that we did is that we aim for a dense consolidation approach. So all these 2,000 VMs now are running, all the workloads that were running on these 2,000 VMs are only running on 7 hosts. So these have some benefits and have some drawbacks. So of course, the main benefit is the higher utilization you can get from your infrastructure, and also managing a much smaller in scale number of nodes is quite easier. Even though we have everything automated for provisioning and configuration management, it's still much simpler to do this. And it has some drawbacks as well. So of course, the impact of having one host failing is bigger because you're running more workloads. And well, we have some issues with Docker engine, and we don't really recommend you to go this way without doing some specific tweaks, because as now, there are some issues when you run more than 100 containers per node. So if you're interested, we have set up a hallway track where we can discuss in depth more about running more than 100 containers per node and share our practices and compare notes with you. So far, 50% cost reduction, it seems like a fairy tale, but this is what the move to Docker really looks like. So as you can see, this picture is from Daniel's story. It's called The Enterprise Journey to the Cloud. And we can see Dragon and sysadmin, DBAs, senior developers trying to tame it, project managers dying in the process, and cloud architects from the far throwing some magic. So there are, of course, some hiccups that we have to overcome. It's not that easy to move to Docker. And Łukasz is going to talk about some of the challenges.
Okay. Thank you, Matthias, for this introduction. And as Matthias already mentioned, I want to describe some of the challenges that we faced when moving to Docker. During this session, I'm not able to describe like even the most important ones, but we chose 2 of them, and I hope that at least these 2 will be useful for you, especially if you're into Dockerizing legacy applications. So let me start with performance and resource sharing. We as a team, we provide a container as a service, or in other words, Docker API to our clients, which are other teams working for the company. And when you run a shared Docker host where there are multiple tenants, multiple clients using the host, you will run into performance problems sooner or later. And you will quickly notice that your biggest enemy in such environment is so-called noisy neighbor, right? The noisy neighbor is either a single container or a small group of containers that is trying to use a lot more resources than all the other containers do. So you can have just like a single container that is trying to eat all your RAM, that is trying to get all the CPU power that it can get from your instance, from your server. And as a result, it can jeopardize your whole host, right? It can make your memory to be swapped. It can get your applications to be starving for CPU time, and so on and so on. And even a single container can make the whole instance fail. Fortunately, from the day one, part of the Docker was to allow for limiting the resources that a single container can use. So using Docker, when you start a container, you can, from day one, as I said, you can limit the resources. You can set limitations on CPU, on memory, and on I/O. So like 3 core concepts, 3 core resources that each computing instance has. But you have to remember a few things. The most important one is that containers are not virtual machines, right? So when you run a virtual machine, you can have your resources divided into different subpools, and then these subpools assigned to a virtual machine through a hypervisor. And then this virtual machine, it runs a kernel of its own. And this new kernel, it sees only the resources that were assigned to this virtual machine. So it can't use more, because everything it sees, everything it can use, is what you configured the virtual machine to have. But with containers, it works completely different. Containers are actually like just regular processes running on your host. They see everything your host has. So they see the whole memory, they see the whole CPU that it has. So the resource limiting mechanism, which is called cgroups in Linux, is not a hypervisor. It doesn't make your resources pooled and virtualized. It more like works like a watchdog. When your container is over the resources, the container will be stopped. So your container sees all the resources that a host has, the whole RAM, the whole CPU. It's just when it tries to use more when you set the limits, it will be either paused, so it won't get any CPU time in the current scheduling round, and it will be paused. Or if it exceeds the memory, it can be like, terminated. At least one of the processes can be terminated by out-of-memory killer. And like the most vivid example over here is JVM, Java's virtual machine. When JVM is starting, it actually checks, and it's pretty cool and pretty smart thing to do. It checks the resources that your host has to offer. So it checks how much memory do you have, how many CPU cores do you have, and it tunes some internal configuration parameters of the virtual runtime to adjust to these parameters. Okay? But the problem is that when JVM is starting inside the container, there are some changes currently to this process, especially for Docker. But in general, up to now, when JVM was starting, it was checking how much memory the host has, it was checking how much memory it has, and how much CPU, and it was adjusting to this. And that's a disaster, because you probably set the limits for a container that is running the JVM to much lower values. So your JVM will be totally misconfigured for this environment. So you have to remember that you have to manually tune your JVM to run in a limited resource Docker container. But all in all, we can take this to a simple conclusion that you just need to always set resources for your containers. It might also include some tuning of the software that is running inside the container, like with JVM. But all in all, if we want to avoid a problem of the noisy neighbor, it should be enough to set resource limits on all the containers. Just by the way, I really wanted to stress this at this specific moment. You also should always label your containers. And you might be wondering why. What does it have in common with performance at all? And what does it do here? But the case is that when you hit a problem, especially in production instance, and you have to react quickly, and you have to debug and resolve the problem quickly, you want to get as much metadata about the container that you suspect to be causing problems, or while it's overusing resources. You want to get as much metadata as you can. So you want to get release stage, you want to get owner information, you want to get product it belongs to, a service it is offering, and so on and so on. And labels are always with the container. So you can't really miss them. If they are assigned, they are there for you to make your life easier. But the problem we faced over here for both resource limiting and for labels assignment was actually the same. We are just offering the platforms. And both resource limits and labels are things that the user is giving to Docker when he or she is starting a container. So the key question over here is how to make your users comply. How do you make your users to actually set resource limits and set labels on a container? And that's the problem that we call configuration compliance. So how to make your containers that are running on the machine to be compliant with some configuration policies. And for that reason, we developed a tool. It's called Docker Enforcer, which is pretty simple in its assumptions. So it just checks all the containers that are running on a given Docker instance, and it checks them, validates them against a set of rules that you as host admin provide. Okay? This is open source tool. You can check it on GitHub, and well, I invite you to do so, check the tool, and maybe help us develop it further. But right now, let me give you some examples of how it can be used and what it can do. Okay, so let's imagine you're running a shared Docker instance, and your users are starting different containers there, and, well, you prepared a nice big storage for them because you know there will be a lot of data coming in and out of these containers. So you, as a host admin, you send this email. Okay, that says, listen, everybody, we prepared a nice big volume for you. It's mounted under /opt/big. Please use it for all your container needs. And let's see what can go wrong. Matthias, can you play a role of our user, and let's see what happens when a user runs a container, okay?
Sure. Let me do that. Okay. So I will check my super big data container over here. And I'm complying with the rules, right?
Yeah, okay. So our user was using our host, that's what it is for, and now we have a problem. Okay, can you spot the problem? It's a typo, right? He was expected to mount his container under /opt/big, but we got just /optbig. As a result, you will probably pretty soon run out of disk space, because this is going to be mapped right now and mounted on the root volume instead of the volume that was prepared for data storage. Okay? So probably your root volume will run out, and someone will get woken up in the middle of the night to fix a problem that the root volume is out of disk space. So how we can prevent this? Not solve, but prevent in the first place. So we got a small demo for you. Rules in Docker Enforcer are delivered as Python lambdas. So this is a set of Python lambdas that have name, and for each of the rule, there's a lambda that is of type kill rule. So this rule, if it evaluates to true, it means that the container should be killed. If it's false, then it's fine for the container to run. So what it does over here, it returns false, so don't harm the container, if it's not using any binds. So if the binds parameter of host config option is empty. Binds are binds between what Docker container sees as a volume and a directory on your hard drive. Okay? In another case, when there are some binds and the container is trying to configure some binds, we will kill this container, so we won't allow it to run if any of the binds does not start with /opt/big. So let's apply this rule. Okay, now it's used as a acting rule set. We need to restart the service, and let's get back over here. And we can't run this container anymore. Okay, we got a message. Your command was denied by plugin enforcer, and as a reason, you get the name of the rule that you have broken. So you must use valid dirs for volumes. Docker Enforcer also provides a simple web API and JSON and web API where you can see the rules. So your users, if it is stopped and a user is wondering why, because he only gets the name of the rule, he or she can easily check this over here. We also have some additional information, like who and when was detected to violate a rule. So by setting this simple rule and using this simple daemon, we just prevented an outage that was based just on a simple typo that will happen sooner or later. Okay, so let me show you another quick example. We talked a while before that you should always set your CPU and memory resource limits for containers that you want to run, right? So how can we enforce this? How can we enforce our users to always provide this option when starting a container? So let me show you another example. This one is a little bit more complicated. Actually, we have two rules over here. This is the first rule. It checks if the container is not trying to use more than 1 GB of memory. So we are checking if the memory parameter is set to 0. 0 means unbound. So the limit was not set at all, and it can use as much as it wants. So in that case, we want to kill the container. Or it was set, but it exceeds 1 GB. The second rule, it checks for CPU usage. In this case, we are trying to limit the container to use just 2 CPU cores. So again, we are checking if it is set to 0, so no restrictions were given. Or we are checking if the ratio between the configured quota, CPU time quota for the container, and the CPU period constant is bigger than 2. If it is, then we will stop such a container. Okay, so let's apply these rules. Okay, and let's run a container. And we got information that we have violated 2 rules, one about memory limits and one about CPU limits. We can try to fix this by complying with what admins are requiring. So we will set memory limit and we will set CPU quota. And now your container runs just fine. Okay?
Okay, thanks, Łukasz. So we've seen how to solve these noisy neighbors issues with configuration compliance. And of course, you can also add some other rules for having all your containers to require labels, so you can know which are the owners, as Łukasz mentioned, and any other rules that you find suitable for your environment. So there are also other legacy applications might have different requirements. So when we are running HTTP apps, we can use reverse proxies, and we can several solutions there. But when we have to run some of the old friends in our containers, like FTP, SMTP, or SIP protocols, we also need to care about the outgoing connections, and also, in general, some of these applications require a specific IP address. For instance, if you have an SMTP server that has some reputation and you want to keep it, you will need to be able to route the traffic properly. Also, there are some additional requirements. You have, for each interface on the host, you have a limit of IP addresses in AWS, for instance. And you might require, in order to run multiple applications on the same host, to be able to use additional interfaces. So, Łukasz, it would be fine if you could explain a little bit about the Docker networking model and what are the things that work but do not work and how we can work around that.
Okay, sure. So to get better insight into this problem, let me just now do a short recap how Docker networking works by default using the bridge driver. Okay, so over here we got a very basic and default setup that Docker prepares for your networking stuff. So we have just a single container, and as Matthias said, often we want just a single specific IP address to be mapped to your single specific Docker container. And like Matthias said, this is useful in multiple situations. And as we're dealing with mainly legacy applications, this is a day-to-day situation for us. So what we got over here, we got one container, container one, that uses -p option to point to a specific IP address, in this case 10.0.0.4, and then it does a port mapping from port 80 in the host's namespace to port 80 in container's namespace. And what Docker does internally to run all your containers when bridge driver is used, it sets up a software bridge, which is basically like a software Ethernet switch. By default, it's named Docker 0, and it assigns a subnet, just an IP subnet, by default something like 172.17.00/16 to this subnet, and then it gives IP addresses from this subnet to particular containers. In that case, our container has 172.17.010/16. So when your traffic is trying to leave the container, it actually travels through the Docker 0 bridge, and then this traffic is routed on the host. So we check main routing table of the host. There we learn that the default gateway that the host should be using is ETH0. So we pass the traffic to the ETH0 interface on the left, and then the traffic can happily leave to the outside world. There's just one piece missing over here, which is network addresses translation, net. Because this internal Docker network, it's not guaranteed to be routable. Basically, it's a private subnet, so it even shouldn't be routable in the public internet. So we're masquerading that. When traffic is leaving the host, we are masquerading the traffic. So we are choosing one of the IP addresses assigned to ETH0 to use as the new source IP address. And for the traffic coming from the internet to your container, we are using DNet to redirect the traffic from the host's networking namespace into your container's networking namespace. And this just works, right? So if we want to use a single IP to drive traffic to a single container, it's enough to use the -p option, and that's it. So, Matthias, if you would run your problematic container like FTP or SMTP, so what would you do?
Just the same what we did in the first case, right? So I will run docker run -p. In this case, I want to use one of the IP addresses on ETH1, so I will just use 10.10.02 and expose port 80. And I will just expect that Docker will make it work for me.
Yeah, and that's pretty valid assumption, right? It was working for the container 1, so it should also work for container 2 that is trying to use IP address 10.10.02 that is assigned to ETH1, so the interface on the right. The problem is that it doesn't work. Why? Because by default, we still have the same workflow. So packet flow, okay, traffic flow. So we get traffic from ETH0 in container 2. This goes through the Docker 0 bridge. Then the default routing table is checked, and this table says that our default gateway is still through ETH0 interface. So traffic tries to leave through ETH0 interface. And that's the first problem. Depending on your actual configuration, like your cloud services provider and so on, this might be already bad and it might not work. Because the IP address, the source IP address that the container will be trying to use is not actually assigned to ETH0 interface, right? So someone might say it looks a little bit like IP spoofing. But even if it does, even if that packet successfully leaves to the internet, it won't come back because it will be directed back to the ETH1 interface because this is where the IP address is actually assigned. And no stateful firewall will allow this to pass because this packet is now out of context. One packet went through ETH0, but the answer is coming through ETH1, and this won't work. So what's the solution? Actually, the solution is already included in Linux kernel, and all you have to do is just to configure it properly. The thing is that we can use multiple routing tables. We are not really forced to use just the one single main routing table. We can create additional route tables, like a table named 101 over here, and then we can make our container to check this new routing table instead of the main one. So we need two things. We need a new routing table that will point to the ETH1 interface, and then we need some mechanism that will allow us to say that traffic from container 2 should be checked against the new routing table, not the old one. Okay? And all of this is already included in the kernel, and we have a ready recipe for you. So if you will find yourself in the same situation, it's pretty common in AWS where you have a limit in general like 30 IP addresses per interface. So when running legacy applications, you will sooner or later have to use additional network interfaces. Then you can use a setup like this. So we're starting with configuration of just the ETH1 interface. We are just assigning the IP address. So in this case, 10.10.02/24. And then we are just adding some very simple root entries to the local subnet and the default gateway route. But we are adding them not to the main routing table, but to a new routing table called 101. That's what this suffix table 101 does in comments in line 2 and 3. And then we are adding routing rule, which says which routing table should be used when. So we're adding a rule that says when traffic is coming from 10.10.02, please use table 101 for routing, not the default one. And then when you start your container, you have to take into account that this is a separate subnet. So Docker created a new subnet, right? The one that includes Docker Zero Bridge. So we have to include this in the routing table, information about this local software subnet. So we do. We add an entry in the routing table for 172.17.00/16 on device Docker Zero. And then we just say, add a new routing rule that if traffic is coming from a container with IP address 172.17.020, use the table 101, not the default one. And one last step, we have to add an IP tables rules that says that for traffic going out from this container, we want to use snat, so hide the source IP address, and replace it with the IP address that we want the other world to believe that is assigned to the container. Okay? So that's already a recipe you can use if you are in the same situation.
Okay, thanks, Łukasz. So just to do a short recap, we have shared some of the outcomes that we can get, especially the increased utilization from 5% to 72% by using this dense consolidation approach. Also, this allows us to decrease our infrastructure costs in a huge number. And well, we've discussed some of the main challenges. Of course, there are more. You have to help your team to adopt the new workflows that Docker imposes. And you have to deal with monitoring. And well, in the conference, there are many talks that are specific about different problems. So we'd like to share what is on our roadmap right now. So first of all, we are on a quest of Dockerizing everything, right? We have multiple AWS accounts for our products, and we want to move everything to run on Docker. So our goal is to have 0 VMs running out of our container as a service platform. As you might have seen, we use this simple Docker approach, and it yields great amount of business value. But of course, we want to also keep improving. So we want to build this platform for stateless containers. We want to help our ops team by adding orchestration. And we want to increase the uptime by using our multiple availability zones. We also think that we can keep getting more cost savings by using AWS Spot instances for this cluster. And well, we are planning to do some investment in re-engineering the apps that are non-Dockerizable right now so that we can move them to Docker, and also invest from the apps that are legacy today and they are stateful in some way, and we will not be able to run in a cloud environment. So we also set up 2 hallway tracks. If you want to join, we have the links on the slides. I am going to share them on Twitter if you're interested, to discuss Docker Enforcer and learn more how you can use it. And also some of the things that we have done to run more than 100 containers per node and to deal with the issues. Of course, we are hiring. There is a link there as well if you want to apply. And well, we have some time for questions. You want to ask a question?
Thanks for the speak. Quite good. I would like to ask about Docker Enforcer. So I saw cases about memory and CPU. And what other things we can check with Docker Enforcer?
Basically, you can check anything that relates to containers configuration options. So anything you pass to Docker run command through CLI, or anything that your application that uses Docker's API sends through to the start and run API endpoints, everything can be checked. So you can write it's a general Python Lambda, so you can check anything, any option that is provided by Docker inside the API. It runs as a Docker authorization plugin, so anything that Docker passes in this authorization call can be checked for. Additionally, you can also check any API requests. So besides of checking what is the configuration of a container that a user wants to start, you can also check what API calls at all globally, all Docker API calls are passing through the service, and you can also deny them or approve, well, up to your needs.
Sounds great. Thank you again.
Thank you. So, any other questions?
Okay, thanks very much.
Thank you very much.